these two molecules on the right, CH4, and on the left, C4H10, are hydrocarbons, and they're both gases at room temperature. Okay, the one on the right is called methane, the one on the left is called butane. You probably know methane from being a main component of natural gas, which we use for our Bunsen burners here. There we go. Okay, and butane is actually what I use for this lighter here. Okay, it looks like a liquid down here because it's pressurized, but when I push on this switch, I'm releasing the gas, which I can light there. Okay, so I just push up on the switch, I'm releasing the gas, which I can then light, okay, to show I'm not using a liquid here. Okay, so these are both gases at room temperature. But interestingly enough, if you take off a couple hydrogens and replace them with oxygen atoms, you get two substances that are liquid at room temperature. This is basically the same as this, except we swapped a couple atoms. Okay, we end up with something that holds together as a liquid. Okay, these two molecules, okay, are very similar, but these guys just cannot get away from each other and end up as a liquid at room temperature. Okay, same thing for our butane, which is very similar to this molecule right here, except this guy cannot get away as a gas either. It's stuck together as a liquid. All our molecules can't escape each other at room temperature. Okay, so this was methane. This guy here is called methanone, or also generally called acetone. Okay, this guy here, was butane. This guy is butanone. All right, or you might see it commonly in like stores and stuff as methyl ethyl ketone, or MEK. Okay, so both of these are good solvents, and they're used for paint thinning and things like that, solvent and cleanup and stuff like that. And to do that, they both have to be liquids. Okay, so these molecules hold together better than their oxygenless counterparts. So let's try and figure out why. Why is that oxygen makes such a big difference here? Between two of these CH4 molecules, or methane molecules, all we really have going for us is dispersion forces. We have one nonpolar molecule of CH4 that happens to get a little bit more of its electron cloud kind of shifted over to one side, so it's a little more electron dense. So it's got a partially negative charge somewhere. And then we've got another molecule of methane that can have its electron cloud kind of polarized and induce a dipole on this. So instantaneous dipole, induced dipole means dispersion forces. These are relatively weak attractions, so this doesn't do a whole lot for keeping things together. So most likely these molecules are going to be free to roam around, and the attractions are going to be very fleeting and weak. They don't resort to much. Okay, same goes for bigger molecules. Since they have more surface area, our butane molecules will have a stronger attraction, and they'll have a boiling point that is a little closer to room temperature. It's a little bit higher. Lower. I always get that mixed up. It's going to be more like a liquid in terms of that, and sum it up. But still, all we have is dispersion forces. We have more dispersion forces because we have more molecule to kind of polarize the electron cloud, but an instantaneous dipole, induced dipole is still fleeting and weak, and these gas particles are not going to be able to attract to each other enough with these intermolecular forces to hold together as a liquid. So what's different? Well, with an oxygen atom in there for a molecule like acetone or methanone, like this guy, okay, we have a permanent dipole. Okay, the oxygen is more electronegative than the carbon, which pulls the electrons kind of more to this side, towards the oxygen. So we end up with a partially negative side, and down by the carbon and the hydrogens, it ends up a little more partially positive. So we have a dipole, okay? If we go and bring that towards another molecule just like it, that has the same situation, it's also a dipole, we have an attraction between the partially negative and the partially positive sides of these molecules. So a permanent dipole and a permanent dipole come together to attract to each other with an intermolecular force we call a dipole-dipole force. Okay? And that is going to be inherently stronger than something that relies on some instantaneous or induced dipoles. They don't last forever. They kind of end up going away. It's in the moment. these stick around, okay? So it's just a matter of keeping our molecules close enough to each other. And that attraction ensures that. We end up with this attraction that is now stronger because we have more kind of partially negative and partially positive charge that sticks around, and therefore we can keep this attraction going. So this ends up staying as a liquid with their particles closer together. Okay, and the same would go for butanone or methyl ethyl ketone, which I don't have the pictures drawn out for, but I can go look at the models. Okay, so this would be where our kind of electron dense area of the electron cloud is, a lot more partially negative charge up here. So if we were to bring another molecule in, if I can keep it from breaking, let me see if I can stick it back together. Oh, I might not be able to lift this without it falling apart. Let's see. There we go. Okay, so down where my thumb is right here, we've got more partially positive charge. We've maybe got a little bit more dispersion forces here on the nonpolar ends of the molecule, but this is a fairly decent dipole with this carbon down here where my middle finger is, where I'm shaking right there, is partially positive. Okay, and this is partially negative up here. So this partially positive carbon is going to attract to the partially negative oxygen right here, and there's an intermolecular force. It's a dipole-dipole force, which again is stronger than the dispersion forces between butane, the just C4H10 molecules with no oxygen in there, just all nonpolar stuff. So this will hold together as a liquid.